we examine the orthogonal projection of vector v onto vector w. We will divide into three cases. Case number 1 is when theta is an acute angle, or theta is between 0 and pi over 2, excluding the endpoints. We draw a sketch. Both vector w and vector v start at O. From the terminal point of vector v, we drop a perpendicular line to meet at R on vector w. The angle between the two vectors is theta. We call the vector OR as vector P, just using a single letter. This vector will consist of the magnitude, which is the magnitude of vector P, and the direction of vector P. We use a little hat over P. Since both vector P and vector W are going the same direction, we can rewrite it as the magnitude of vector P times the direction of vector W. This is a right triangle with theta, and the hypotenuse is vector V, taking the magnitude of the vector, and adjacent to theta is the magnitude of vector P. Cosine of theta equals adjacent over hypotenuse, which is the magnitude of vector P over the magnitude of vector V. Multiplying both sides by the magnitude of vector V, we have the magnitude of vector V times cosine of theta equals the magnitude of vector P. We can substitute it back in the previous equation. Then vector P equals the magnitude of vector V times cosine of theta times the direction of vector W. We want to convert this expression in terms of dot product. So we multiply inside the parentheses by the magnitude of vector W over the magnitude of vector W. Then vector P becomes vector V dot vector W over the magnitude of vector W times the direction of vector W. Vector W divided by its own magnitude is the same as the direction of vector W. Then we have vector P equals vector V dot the direction of vector W times the direction of vector W. The second case is when theta is a right angle, or theta equals pi over 2. We have both vector V and W having the initial point coincide at O, and the angle between the two vectors is a right angle. If we drop a perpendicular line from the terminal point of vector V onto vector W, then we will have the intersection point at O also. So if we define vector P the same way, then vector P equals O, O. That's a vector from O to O, which is a zero vector. We know that when the two vectors are orthogonal to each other, which is vector V is orthogonal to vector W, then the dot product vector V dot vector W is 0. And vector V dot the direction of vector W is also 0. Then vector P, we can define it the same way as before, equals vector V dot the direction of vector W times the direction of vector W. Because vector V dot the direction of vector W is 0, and 0 times the direction of vector W is a 0 vector. The third case is when theta is an obtuse angle, or theta is between pi over 2 and pi, excluding the endpoints. We draw a sketch again. Both vector V and vector W will have the initial point at O. We drop a perpendicular line from the terminal point of vector V onto the extension of vector W and call that point R. The angle between the two vectors is theta, and the supplementary angle of theta is theta prime. Theta plus theta prime equals pi because they are supplementary angles. Or we can call theta prime the reference angle. Then we define vector p the same way, equals OR equals the magnitude of vector p times the direction of vector p. Since the direction of vector p is opposite to the direction of vector w, it equals the magnitude of vector p times negative of the direction of vector w. We again look at the triangle itself and examine the length and angle. We draw a right triangle and we put theta prime there, and the adjacent to theta prime is the magnitude of vector p, and the hypotenuse is the magnitude of vector v. Since theta and theta prime are supplementary angles, cosine of theta prime equals negative of cosine theta. On the other hand, cosine of theta prime equals adjacent over hypotenuse, which is the magnitude of vector p over the magnitude of vector v. Using cross multiplication, we have the magnitude of vector p equals the magnitude of vector v times negative cosine of theta. We substitute it into the previous equation. Then vector p equals the magnitude of vector v times negative cosine of theta times negative of the direction of vector w. Negative times negative is positive. Vector p equals the magnitude of vector v cosine of theta times the direction of vector w. Again, we want to use dot product to represent this expression. We multiply inside the parentheses by the magnitude of vector w over itself. Then vector p becomes vector v dot vector w divided by the magnitude of vector w times the direction of vector w. Vector p equals vector v dot the direction of vector w times the direction of vector w outside the parentheses.